Before starting off with the course, I will give you an introduction to HVAC systems. Refer to the system shown. There are three main sections involved in this system. They are cooling system, heating system, air handling unit, AHU. The cooling system is used to reduce the temperature of the environment that the HVAC system is controlling. The components of the system are chiller, cooling tower, condenser pump, primary pump, secondary pump. Let us move on to the heating system. This system is used to increase the temperature of the environment that the HVAC system is controlling. The components of the heating system are boiler, primary pump, secondary pump. The third section is the air handling unit. The AHU controls the ventilation and temperature in a building by controlling the airflow capacity. The components of this section are cooling coil, heating coil, air filter, ductwork, supply fan, return fan, inlet damper, exhaust damper, return damper. Let us now see how cooling is provided by this system. The warm water rejected by the chiller is sent to the cooling tower through the condenser pump and cooled. This cooled water in the cooling tower basin is pumped onto the chiller. The secondary pump pumps the chilled water from the chiller to the cooling coils. Fresh air blows in from the inlet damper. This air flows across the cooling coils and its temperature is reduced. The water in the cooling coil takes up the heat from the fresh air blown through it, and this warmed water is sent back to the chiller by pump for chilling. The chill air flowing out of the cooling coils is moved into the ductwork by means of a supply fan. Through the ductwork, chilled air is distributed to the individual zones. The warm air in the zones are sent back through the return fan. A part of this air is sent out as exhaust. The other part is fed back into the system through return dampers to be used for cooling. In case the process is that of heating, the hot water from the boiler is fed to the heating coil by means of the secondary pump. The water passes through the coil, and it is returned to the boiler. The rest of the flow is same as in the case of cooling. Let's start with the first module. By the end of this module, you will have a basic understanding on VAV application, how it works traditionally in Danfoss solution, the key benefits of using a VLT HVAC drive in VAV systems. Let me begin by explaining a VAV system to you. Central Variable Air Volume System is a variable air handling system. A central variable air volume system controls the ventilation and temperature in a building by controlling the air handling unit's airflow. That is, the chilled air is distributed to the spaces from an air handling unit, and the temperature of the individual spaces are controlled by throttling the quantity of airflow into each space. But how is this done? Let us refer to the system shown. VAV systems typically bring outside air into air handling units and mix with return air where the air temperature and humidity can be adjusted. Central fans blow the air across cooling and heating coils into ductwork, which distributes the air throughout the building to all the individual zones. The air passes into each zone from the ductwork through individual VAV boxes. A temperature sensor, located in each zone, modulates the VAV box damper to maintain a temperature set point. The system is designed to maintain constant static pressure in the supply duct and a positive building static pressure by regulating the airflow of the supply and return fans. The static pressure sensor in the ducts transmits a change in pressure to the discharge damper, R, inlet guide vanes, through a controller, and the fan capacity is varied to maintain constant static pressure. The fan speed remains constant. Central VAV systems are considered to be the most energy-efficient method to air-condition buildings, because reducing air volume saves both fan motor energy and energy involved in heating or cooling air. Now that you have had an overview of VAV systems, let's go in for a quick check. That's right. Fans blow the air across cooling and heating coils into ductwork. The air passes into each zone from the ductwork through individual VAV boxes. That's right. VAV systems are used to control the ventilation and temperature in a room. I hope you are now familiar with the application. Let us proceed to see its working. Consider an air-conditioned conference room that is going to house a meeting. Why don't you add some people to the room? As the number of people in the room increases, the temperature of the room increases. The VAV system will work to bring the temperature of the room back to the set point. Let's see how this happens. See here, there is a sensor tracking the room temperature. This temperature sensor modulates the VAV box damper to maintain a temperature set point. As the VAV box modulates, the static pressure in the ductwork changes. Can you tell me why? Here is the reason. When the temperature reaches the set point, the box is closed to restrict airflow, and this results in an increased static pressure in the ductwork. In the traditional method, the static pressure sensor in the duct transmits this change through a controller to the discharge damper, or IGV, and thus the fan capacity is varied to maintain constant static pressure. But the fan speed remains constant, resulting the system to work at a lower efficiency. In the traditional method, I mentioned two different ways of modulating the fan capacity, that is, controlling airflow. Do you recall? One way is by using discharge dampers. The other is by using IGV. We shall see each of these two methods in detail. First, let us consider the usage of discharge dampers in modulating the fan capacity. Discharge dampers reduce airflow by creating resistance and a pressure drop across the fan. But, in this method, when the fan moves up the fan curve, the motor power changes very little, and less energy savings occur. There are more energy-efficient means of controlling fan capacity. Refer to the graph. It consists of the fan curve and system curve. As the VAV terminal box modulates closed, the system curve shifts upward on the fan curve from point A towards point C. The static pressure digital controller senses this increase in pressure and modulates the discharge damper closed, thus reducing fan volume and bringing system static pressure back to the set point. The fan motor runs at constant speed, so minimum input power savings are achieved by this method. Verify this with a graph. Next, let us consider the modulation of fan capacity using an IGV. IGVs reduce airflow by pre-spinning the air entering the fan. As the VAV terminal box modulates closed, the system curve shifts upward on the fan curve, as in the case of discharge dampers. What does it mean? As VAV box is close, the duct static pressure increases, and the fan static pressure increases as the fan rides up its curve. The duct static pressure controller senses this change, and sends a signal to the inlet guide vanes, start to close. Look at the graph. You will find that a new series of fan curves are generated, and motor power is reduced, and the fan delivers lower air volume. Reducing fan volume and fan static pressure brings the system static pressure back to the set point. But, like in the case of discharge dampers, the fan motor runs at constant speed, and so only moderate power savings are achieved by this method. You can verify this moderate energy savings from the graph. Also, both discharge dampers and IGVs are mechanical devices, requiring regular maintenance. The power savings achieved is more when IGVs are used to modulate the fan capacity than when discharge dampers are used. This is because pre-spinning in the IGV reduces fan power requirements. Usage of a VLT HVAC drive is the Danfoss solution. Instead of creating an artificial pressure drop like in the case of discharge dampers or IGVs, the VLT HVAC drive decreases the speed of the fan to provide the flow and pressure required by the system. Centrifugal fans follow the affinity laws. This means that power is significantly reduced when fan volume is reduced. Let us consider the same case of the conference room with the people. The sensor tracks the room temperature and modulates the VAV box damper to maintain a temperature set point. As the VAV box modulates, the static pressure in the ductwork changes. I have already given the reason for this. Can you recall? If not, let me repeat it again. When the temperature reaches the set point, the box is closed to restrict airflow, and this results in an increased static pressure in the ductwork. The static pressure sensor signal is transmitted to the VLT HVAC drive, and the fan speed is varied to reduce volume and maintain a constant static pressure. As VAV box is close, the duct static pressure increases, and the fan static pressure increases as the fan rides up its curve. The duct static pressure controller senses this change and sends a signal to the VLT HVAC drive, and the fan thus deliver lower air volume at a higher static pressure. A new series of fan curves are generated, and motor power is reduced, and the fan delivers lower air volume. Refer to graph. Reducing fan volume and fan static pressure brings the system static pressure back to the set point. Thus, with the VLT HVAC drive, the fan motor runs at variable speed, and so maximum power, kilowatt, savings are achieved. Here is a summary of the three methods of airflow control. Let us consider the case of temperature rise in a room, due to increase in the number of people. The HVAC system works to bring the temperature back to the set point. In the process, the pressure in the ducts is brought back to its prescribed value by controlling the airflow from the supply fan, and this can be done in three different ways. Here, you can compare the efficiency of each of these methods through their respective graphs. Click on each of the controls and see the energy utilizations. You will find that in the Danfoss solution, where a VLT HVAC drive is used, there is considerable energy savings when compared to the traditional method. A study of the energy savings shows that discharge dampers offer 10% savings, IGVs offer 40% savings, and VLT HVAC drives offer 70% savings. Is the advantage of using VLT HVAC drive clear to you now? To summarize, a drive solution saves more energy than discharge dampers or IGVs, and also eliminates the requirement for mechanical maintenance. An advanced feature of the VLT HVAC drive is its ability to accept two input and set point signals. This allows the use of a second static pressure transmitter to control supply fan capacity. One sensor controls fan motor speed based on duct static pressure. The second sensor operates as a high limit to prevent damage to the ductwork or components. The VLT HVAC drive has one more key benefit. A new built-in time clock allows scheduled start-stop of motors and time date stamp of events. This provides time scheduling of the fan when a building management system, or time clock does not exist. Another illustration of better control by the VLT HVAC drive is seen here. The VLT HVAC drive adjusts the speed of the motor based on the varying requirements during the day. This shows a fan speed schedule, where the fan starts at 7 and runs at 100% speed. At lunch, the speed is reduced to 60% because of lower occupancy. At 15 the speed is reduced to 40% because of lower occupancy, and the fan is stopped at 18. These speed changes provide additional energy savings to the savings provided by the VLT HVAC drive. We have completed the model by now. You must have gained a good idea of VAV applications in general, their working, traditional and Danfoss solution. Benefits of using a VLT HVAC drive for airflow control.